Well, it's a pleasure to be here. It was a bit spontaneous, actually, appearance. So it's very nice when it comes along like this. So thank you to the organizers, Anthony, Mathilde. I'm enjoying it so far, so my mind might be a bit scattered by the fluids right now, just nearby, the waves. But I'll try to keep it coherent. So the topic that I'd like to talk about today is essentially how the high near-lithostatic pore pressures or conversely very low effective stress along faults can be generated and maintained by the upwelling fluid flow. So both in the laboratory and in nature, and of course we are motivated by nature. And then what it might mean for the seismogenesis on faults that hosts such flows. And so this work has been started some time ago, and Nicola keeps reminding me about that, and Roma as well. But so these are the collaborators, and Alex Shubnel and Harshabat from École Normale Supérieure. Sounds like misnomer, normal and superior, no?
I'll explain later.
Okay, and we'll talk about it later. So anyway, well, the moment, the time I was sort of got interested, my personal interest in that problem was sort of spurred by this apparent quandary of slow sleep at the base of San Andreas faults, and I think some of the suspects that introduced this into the field maybe around here or related to that. But essentially, there was an observation back in maybe late 2000s that so somewhere between 15 to 30 kilometers, so all the way to the perhaps roots of the San Andreas in the upper mantle, that you observe these LFEs and inferred slow sleep that apparently is triggered by very small tidal perturbation of background shear stress. And then the inference is that you need a very low effective normal stresses and therefore strength. So by some people estimated of the order of 1 MPa. So at the 15 to 30 kilometer depth, for this to be able to happen. So what is the possible mechanism that could allow for such a low resolved effective normal stresses at the lower half of the San Andreas? And so there is some history to that question, and I'll talk about in a bit more detail, but this is sort of a quick eagle's eye view motivation. So there've been an evidence of the volatiles all the way from the mantle upwelling along major faults, including San Andreas. So faults serve as conduits for the volatiles that want to escape from the mantles, and the volatiles typically are water, CO2, I think these are the two major ones. And this evidence came from geochemists, and I'll talk about that. And then from the mechanics of the source and hydromechanics of the fluid flow. So Jim Rice in '92, and I think Byerly as well, maybe a little earlier, had this idea that the stress-dependent permeability to get coupled with this source of the deep source of the flow can produce overpressure. However, what we will see that this mechanism, at least the way it was posed by Jim, cannot explain the near zero effective normal stress. It essentially produces a pore pressure that tracks which gradient with depth tracks the lithostatic, but at a fixed distance away, and that distance is the effective stress. And so it's typically of the order of 100 MPa, meaning that effective stress no longer increases, it plateaus with depth, but it is very much material value that would not allow what we see. And so the quandary is, how is that possible? And so there is a possible answer, but I'll go into it, and it has to do with some time history of how the flow developed and the hysteretic nature of the dependence of permeability on the effective stress. But there are, so, and out of this initial motivation came, but once you start talking about regimes of pore pressure, then I'll be talking about long-term regimes, or maybe averaged over a long time. So I'm not going to be talking about episodic fault valve in action. It's, if you want, averaged out over long-term average regime, right? And so what are the implications of some things that come out of this for the general fault strength with depth, and then, you know, how does, could it push the, what is typically considered the transition to ductile flow, could it push it all the way down to the, you know, further down to the roots? So meaning, could the strands be everywhere frictional over the known crustal depth of the faults? What does it mean also for seismogenesis and the tale of the three creeping faults by Professor Jolivet? So we'll start with the evidence of the mantle volatiles in the faults. And this evidence comes from geochemists that looked at the trace element. So the mantle is rich in one particular isotope of helium, which is helium-4. And the crust is rich in another isotope of the helium, which is helium-3. Okay, and if you imagine that you have this, if you have the mantle volatiles upwelling along the fault conduit, so they start out of the mantle with this ratio. So R is the ratio of the helium-4, which is mantle helium, you could call it, to helium-3, which is the crustal or atmospheric helium. So atmosphere is rich in. So it starts with the high ratio of the mantle helium, and then it gets diluted by the so helium-3, the crustal helium, is produced in radiogenic crust, and so this mantle helium got diluted from the crust by the helium-3, so that ratio moves decreases, and so then what you measure either at a hot spring at the surface or in the borehole, you measure the values with which somewhere in between crustal and mantle, and the closer they are to mantle, which means that would mean the faster did this flow happen, traverse. So basically, it's a transit time, could be measured looking at it this way. So essentially, you could estimate the flow, the flow rate, the flow velocity, basically by looking how the measured ratio compared to that of the crust and that of the mantle. So you could see that if the measured ratio is that of the mantle, in fact, the denominator is 0, so that means that that the flow is very fast. So it did not get diluted in this crustal helium isotope 3. And if it's very slow, then perhaps it's completely diluted and you don't see the signature of the mantle helium at all. So you miss it altogether, right? So, and so people have looked at the measurements of this helium ratio. Well, this is this original study by Kennedy et al. Along San Andreas. And so here the light color is there is almost no signature of the mantle helium, and the darker color there is a signature. And so this is somewhere Varian Well near Parkfield, so there is a strong signature. It's near the, I guess, Parkfield creeping or partially creeping fault. And then if you go, so there are mixed messages, but you know, on the locked parts you have measurements that have no trace, so perhaps the flow is not that strong there. You can also look at the so such measurements have been done not just on the San Andreas. So here you have actually the San Andreas one and the overall curve drawn, although it connects the dots which may be their own faults that are off trace of the main fault, which is, let's say, for this orange line is a San Andreas one. So you could see all the measurements directly on the San Andreas trace. And you have this converted helium ratio to the corresponding flow rate through this basically transit time, right? So you could see that there is a measurable flow of mantle volatiles on the fault trace. There is literally nothing off fault trace to the one side of San Andreas in this case. And there is a limited measurement, there is small flow, but then there is also a larger one, but this is actually associated with another fault. So there's a splay fault, I think, that on that side of the San Andreas. So perhaps this should be just the distribution that might need to be drawn like this, right? And then the similar measurements have been done on North Anatolian fault. So you have and on KKF is the Karakorum fault. So I think we can be convinced with that there is a fluid connection to the mantle along the major faults that have the roots in the upper mantle. And so using that, well, then you can look at essentially. That's what Jim tried to address first. So if you have a specified flow, which you get from geochemists doing these helium ratio measurements, let's say in millimeters per year, could be 10 millimeters per year. So it's pretty slow flow. And then you have a conduit, a fault, with the specified stress-dependent permeability. And then what Rice in '92 found that if you look at, let's say, stress, and the absolute stress varies here, let's say, over lithostatic gradient, and pore pressure, so near surface pore pressure, in the shallow crust, it follows hydrostatic gradient. But then on the model with this effective stress-dependent permeability, it eventually starts to track the gradient of the pore pressure, starts to track that of the lithostatic stress, and the difference is the sigma bar, sigma minus p is the effective stress, and that's this plateaued effective stress of 100 MP, right? And as we said, okay, that's definitely an interesting implication, and that type of plateaued effective stress profile with depth has been used in many numerical studies of cycles, etc. But it cannot explain the observations of these slow sleeps, LAFEs, etc., triggered by very small perturbations. And so we can turn to the lab first. Let's do that. So we have a little bit of a preview what we want to look at. So we want to look at the fault rock. So we are looking at the fault zone, perhaps the most conductive fault rock unit within that fault zone with the highest permeability. And so that could be a fractured rock, or it could be foliated gouge. Well, we will look at the structures of the faults a bit later. But what we want to then take some fault rock analog and look how it responds to this high pore pressure injection in the lab. And so what we did back in some time ago at ANS, we took thermally micro-cracked granite. So there is a starter granite is here, and thermally micro-cracked is the granite that basically been baked in an oven up to 600, 700 degrees. And because of the mismatch of elastic properties of these polyminerals that form granite, you have intergranular, so you could see them between, right? You don't see the cracks here, so the grains are fused perfectly, and then now all the grains are basically joined over the intergranular cracks, but you also have some intra cracks as well. So it's a cracked granite, but micro-cracked, and it has representative permeabilities which are orders of magnitude larger. And then, so you could take such a sample out of this micro-cracked granite, and you can do the typical classical characterization of the stress-dependent permeability. So you load it by isotropic confinement stress, and then you permeate at a small gradient between the, let's say, upstream and downstream side of 0.5 MPa. And then you can do the loading. So here you have permeability versus so here the label is missing. So this is the effective stress in MPa. And so in this case, it was loaded with confining stress at a fixed low level of pore pressure. So these are the blue dots. And then unloaded from a certain level of stress, which we call sigma p here, which was about 80 MPa maybe. And it was unloaded, reloaded, etc. But essentially, you could identify from here the two branches or hysteretic dependence of permeability on stress. So here you could say you have initial load and permeability branch, or the virgin consolidation, if you want soil mechanics terminology. So the characteristic of it that permeability is being reduced upon initial loading at a high pace with increasing effective stress. So here it could be modeled as a power law to the power of about -2. And then upon unloading, reloading, the permeability upon unloading is regained, but at a much slower clip, right, you could say. So, and micromechanically, it's understood as upon initial loading, you may have closed some of those cracks, micro cracks, right? Or in case of gouges, some of the porosity. And upon unloading, you cannot recover all of that closure because there is a bridging between the sides of the micro cracks, which effectively prevent those cracks to open to the full extent as they were before this loading happened. So there is a notion of the history dependence of permeability, which comes from this maximum load which the rock experienced in its loading history, and or so-called pre-consolidation pressure in the soil mechanics. And I would argue, so why I am spending a bit of time on it, I would argue that becomes very important when you look at what is kind of pore pressure regime has to be maintained in order to facilitate the flow from the roots of the fault up, okay? And we could also, so we have an eye here to conduct a proxy experiment where we specify the pore pressure. So essentially, it's a Darcy permeation experiment, but on the upstream end, we want to apply something which is near lithostatic pore pressure. So we want to replicate these conditions where at the roots of the fault, you have near lithostatic pore pressures, and then up there, you have hydrostatic conditions. So, but what we then would be interested in actually getting the profile of pore pressure through the sample in that flow, right? And at the time that this experiment was done, we didn't have a means to directly measure. We did not have the pore pressure sensors that later were developed that could have been positioned. So we decided we could infer the effective stress and therefore the pore pressure locally by measuring circumferential strain at a number of positions along the sample axis, okay? And so this is what it shows, how we could, this was the calibration of when the uniform through the sample effective stress was applied, and the strain of each of those 8 strain gauges was recorded. So we had this calibration of the uniform stressing and straining, so strain versus effective stress, right? So all those at different level of effective stress, all of those correspond to the response of these 8 gauges. So they are more or less consistent between themselves. And they behave a little bit differently upon unloading and reloading, but still you have a calibration, we would say. So meaning that if during injection experiment where we don't know what is the distribution of pore pressure along the flow, we would be able to infer it by measuring the strain and then inferring the effective stress. So that was the idea behind how to measure the pore pressure. And so then we performed this, you could say, lithostatic fluid pressure injection experiments. So again, it's just a Darcy test in the confined sample, but the upstream pressure is very near the confining. Okay, so meaning that absolute stress is about 80 MPa, while the effective stress is about 3 MPa, right? And so this is the record of this two ends of pore pressure, which is obviously we know from the pump. And so what you see here in the first test, basically the B side is maintained at 2 MPa, while the A side is raised to the 80 MPa. So it's so A is an upstream side, and you have this gigantic pressure gradient which drives the flow. Then it followed by reversal. So we have basically, we reverse the flows. And then you can change the magnitude of pore pressure. You can zoom. So this is the level of confining stress. And therefore, the difference between that level and the pore pressure is the effective stress, right? At the upstream end of the specimen. So if you zoom here, so you could see all these injection tests that we did at the different levels. So P upstream are those different values, approaching within 1 MPa of the 83 value of the confining stress. And so this is the corresponding record of this normalized strain, where each color corresponds to one of those 8 gauges along the axis of the specimen. So that's what we hope to use to recover the effective stress distribution along the flow. Well, and this was the record of the flow rate or the flow velocity. Okay. And generally, so, well, I'm not going to dwell on it, but basically we have the measurement of, we prescribe the pore pressure at the upstream and downstream end, and we have the measurement of the flow, and we can work with that. So we take the strain versus the strain record along the specimen. We can, so that it's copied here. So each of those are the basically strain at the different axial position, different depth or different height along the axis of the specimen. We can use this calibration of strain to effective stress that we got from this uniform pressurization calibration before. And we can recover the effective depth versus effective stress versus depth profiles. And these are 6 profiles for 6 different values of the upstream pore pressure. So the downstream pore pressure is 2 MPa. The stress is 83 MPa. And this is the upstream pore pressure that increased from 42 MPa to something that within 1 MPa of the confining stress, right? So what you see is that for the upstream value, which is about half of the confining stress, so it is still quite a vigorous injection test, right? But not, yeah. So you have some sort of a quasi-linear Darcian thing, implying that perhaps that permeability is more or less uniform, etc. But what you see with increasing the upstream path, you see, first of all, so this is the effective stress that's on the horizontal axis. You see that, well, of course, you are moving towards very small effective stresses, commensurate to the high value of upstream pore pressure prescribed. But what you also see that you completely depart from a linear profile that is typical of the classical Darcy test. Well, you expect it, or you imply it to make interpretation of permeability, right? And so we can focus here. So you have essentially near zero effective stress corresponding to this lithostatic pore pressure value at the upstream end, where the source is of the fluid. and it persists through more than the half of the sample, and then very non-linearly it shoots to the hydrostatic or drain end. Okay. So, well, that's summarized here. So in essence, if this was a perfect analog, which it is not to the nature, like, you know, if this is the root of the fault and this is the surface, well, you have a near zero effective stress and strength, therefore, through the entire bottom half of the crustal fault, right? So before I go further, I should also mention, so Gan-Lin and its work together with Alex Shubnel, etc. So the similar experiments were run again, but this time using the direct local measurements of pore pressure, using pore pressure sensors akin to those developed a little bit earlier by Nicolas Brantou, also in Imperial College, where he worked. So basically, this inference is based on the strain versus effective stress calibration that we had, because remember, we didn't have direct pore pressure, local pore pressure measurements along the sample. So all of this was recovered from our inferences between effective stress and local strain. So this was validated, let's say, or by direct measurements in the similar tests. And so then you can ask, can you actually predict this, this type of behavior with a simple model? And well, the answer is yes. So we take our hysteretic permeability. So, but in fact, the only thing that we need is this unload and reloading branch, because prior to the onset of the flow, when you raise the upstream value of pore pressure to where it should be, you are essentially here. So this characterizes your initial no flux state, right? You are at the peak load at the high confining stress value uniformly through the specimen, and then you apply the very high upstream value of pore pressure. You drop the effective stress at the upstream end to small values. So this becomes your boundary condition at the upstream end. This is still your boundary condition at the downstream end. And then in the flow, you're exercising this entire branch, basically, right? So we could take, if we just look at the steady state flow, so then you can use your Darcy law with measured Q, with measured unloading branch, which is simply 1 over effective stress, you could say, proportional to inverse in stress, to model the profiles that we have. And in fact, so these are the same profiles, the dots, but the solid lines are the modeling part, informed by value of Q measured in experiment, and this unloading branch, 1 over sigma bar, also calibrated in the experiment for a given peak stress, right? All right, so does this translate to nature? Is it grammatically correct, I think? Does it? Yeah. So in other words, can a fault roots fluid source maintain the near electrostatic pore pressure over a large part of the fault? So could that be translatable to nature? So from lab to nature. And here we can first try to bring the nature with all its well, with a little bit of its complexity. So we need to get some notions of what are the fault rocks that conduct the fluid along faults. So you can look at the very sort of a schematic picture of the structure of a fault zone. In this case, it's a San Gabriel fault, inactive, but it accommodated a lot of, maybe it was accommodating, it switched to San Andreas, I think, right? If I'm, yeah. So what we're interested in is permeability, but permeability, of course, relates to these different structural fault rock units that exist. So just generally speaking, you have a core, or you have the central autocatastatic layer, flanked by foliated zone, which is typically viewed as a fault core. So the central ultraclassic layer is super impermeable, but that's what accommodates majority of slip. So it's a weaker part of the fault zone. And then you have variably damaged host rock intermingled with foliated gouges, etc., which form this, the damaged host rock. And then eventually, as you go further away, you recover more or less undamaged host rock, right? And if you look, in this case, it's the investigation for Najima fault. I think it's the one who accommodated Kobe earthquake, right? So you get this very typical schematized, again, profile of permeability with a distance from this principal slip zone. So this ultracataclystic layer is very, very impermeable. So this is permeability in Darcy. So it's 10 to the minus 7 times 10 to the minus 12, 10 to the minus 19. And then you have fault rock units that are quite permeable, and then you again drop the permeability with distance away as you less and less damaged, right? So these fault units with large permeability could serve as fluid conduits, right? If we think in terms of how we're going to transport fluid from the depth. You could look at the similar characterizations of permeability in this San Andreas Fault Observatory at depth, where the San Andreas was drilled through at the depth close to 3 kilometers. And so here you could see that you're going through the fault zone, and there were, in fact, I think 3 slip zones that were drilled through. The south one, the central one, and then north, I guess. And then the core was recovered, and this, as one was drilling through, so as you drill through, that's the depth. So you arrive to the first slip zone, then you continue, then you encounter this serpentinite-bearing clay gouge, which is central deformation zone, and so forth. So you could look at permeability of these different rock units, and you sort of can pick the rock unit which may have, so it's a permeability at 40 MPa effective stress, which might have the largest value, and identify that as the conduit, right? Why I'm talking about it? Because this is the units that we would need to characterize the stress dependence of permeability of to be able to inform our flow and pore pressure regimes. Well, and finally, the one that I'll focus on the most, so I'm not going to spend too much time talking about it, but this was another famous study of the fault and permeability structure for the medium tectonic line fault by Wieberle and Wieberle-Shimamoto. And again, you can, so what you see here, so you see here some geological identification of the different fault units in a very funky depiction, because if you notice, it's drawn on a logarithmic scale emanating from the principal slip zone. But then many tests of those many different rocks were done. So what you see here are essentially profile of permeability at different stress. So you have a permeability upon initial loading at 30 MPa. The loading continued on to 180 MPa. So you drop permeability to drastically, right, like 4 orders of magnitude. And then unloading back to 30 MPa. So here you have your history. So at the same value of effective stress, you have a clear manifestation of gigantic hysteresis, right? And so we'll focus on this particular unit, which we could say is potential fluid conduit. And this is the corresponding measurements by Wieberle and Shimamoto of permeability along the loading branch, up to 180 MPa effective stress, and along the unloading branch. You could also superimpose on it the permeability of that conductive unit from San Andreas fault at depth core. So that's these black circles. So in fact, yeah, okay, I'm not gonna. But well, remarkably, it's a very similar to the most conductive unit of MTL. Just saying, I don't want to really make any big statement, but it's nice that you sort of can translate between the two. And so if you take this description, which is log linear, and you translate it into log-log, well, you find out that permeability, in fact, is the best described as a power law, although many choose to describe it as exponential, as like exponentially decaying with effective stress. But it appears, particularly for the unloading one, that is the power loss is a quite good description. And so for the loading branch K plus, it's a high negative power law, and for the unloading one, it's still 1 over the effective stress. And in fact, this translates over many rocks, many fault rock units, because we will in Shimamoto tested many different across the fault. So if the loading branch may change the slope, but typically the unloading branch is always close to 1 over stress. Well, and you can relate all of that back to soil mechanics. So the engineers have seen it a long time ago. This is the hysteretic behavior of soil in compression. You know, the virgin consolidation versus the unloading, reloading. And so that was for the void ratio, so which translates to porosity, but you can translate it to permeability. Okay, so we'll take that permeability structure and we'll ask ourselves, so if you have an upwelling flow, which we can constrain by these helium inferences, helium ratio inferences, so Q. So we would put it in a Darcy-like law. So we have reformulated it in terms of effective stress, which is sigma minus pressure. So, and sigma is distributed, it has a, let's say, fixed gradient with depth, the lithostatic or double lithostatic, depending on. And so this is essentially is the pore pressure minus the elevation head thing, gradient. And this is your unloading permeability. So imagine the situation that the fault has been in existence prior to being exposed to any flow. So meaning that it has been its effective stress was distributed along lithostatic minus hydrostatic gradient. So very high effective stresses with depth. And essentially with depth, so with effective stress, which translates linearly to depth, right? Your permeability with depth would look similarly and distributed along this loading line. And then imagine that something get underplated, or just make a thought experiment that we open the top of the mantle fluids at the base of the fault, or maybe the fault grown and finally connected to the upper mantle and therefore able to transmit the fluids. Whatever is the actual geological case, since I am a model, I can play a devil's advocate and say, let's consider that. And so at that moment, you're at different depths, you are sitting on this loading curve, and at each given depth, you start unloading along the corresponding different branch, right? And this is basically what's encapsulated here. So this unloading permeability is the function of the actual current effective stress, but it's also a function from the peak effective stress at a given depth, which is depth dependent, from which you unload it to allow the flow through, right? And why? Yeah. So essentially, so if you consider that, and that's the difference from Rice 92. So Rice 92 essentially said that I'm sitting initially on either this or that, but essentially I'm unloading and reloading along the same branch. So there is no hysteresis. Okay. But if you put the hysteresis, So what happens is you can go through the motions. I'm going to skip these motions. You can, in fact, even integrate analytically that ODE. But what you get is this. So this is what you had initially before the flux was put in place. So flux is 0. And then you open the tap at 3 millimeters a year. There is some transiency that happens, which we'll mention a little bit in the next slide. But you evolve to this type of profile. Okay? So this profile is you follow, the pore pressure remains hydrostatic, so you follow this lithostatic minus hydrostatic line to some depth. And then it really wants to unload to allow for permeability that would allow for the flow, because otherwise the permeability, remember, it was along the loading branch, so it's really minuscule as you go down with depth, right? So you essentially, with this hysteretic behavior, you get a profile which is near 0, you could say, through the half of the crustal thickness. And then you have a stress asperity where the effective stress and pore pressure wants to regain the hydrostatic gradient, the effective stress wants to regain this gradient, right? And that forms this, what looks like an asperity, right? Stress asperity. So in the case of the Rice non-hysteretic permeability, you have that. And this is your plateau effective stress with depth. So this just depicts what happens to permeability. So you're initially sitting along this loading line where effective stress is distributed along lithostatic minus hydrostatic, and then you turn on the valve. So you unload from a different point of this loading permeability branch, and this is your final distribution of K with sigma bar. So and I think I'm not going to comment much on that, but this is kind of important bit, and I hope Pablo could see it, because I don't know, it's a good angle. It should have been here. That would be more prominent place. But basically, this, well, if you take anything, take out this out of the stock. So well, one thing, you have a stress asperity with the tail, which is near 0, which, as you could guess already, could allow for this in the mind of theoretician for these low frequency events and slow sleep tidally modulated. But then this explores how this stress asperity depends on the Q, how vigorous is the flux, right? So from 0.1 millimeter a year, almost non-existence, to 10 millimeter a year. So what you could see that this asperity essentially could be characterized by the peak value of stress, so magnitude of the asperity, and by the centroid, right? The sigma peak, sigma bar peak, and Z peak. And those scale as the flux to the minus m, and m being the loading, so it's like factor is a power law of 4, so minus 4. So it's a decreasing function of increasing Q. So with increasing Q, you are essentially reducing the magnitude of asperity, and you are shallowing it, right? And that's, I think, important to remember here. I'm not sure if I have what, 10 minutes, 5 minutes? 10 minutes, that would be more desirable. 7. It always have to be, it can be neither happy or too unhappy, right? Yeah. But that's okay. I'll accelerate a bit. So, well, this slide explores the question, well, how long it takes to develop this long-term steady-state pore pressure effective stress regime. So here this models the transient problem when you turn on the flux and what happens after. So you could see in kilo years, so you arrive to this steady-state distribution. So this actually is shown for viscosity of water of 1, but more representative value would be 0.1 depth-wise. So this would be accelerated to 30 kilo years instead of 300 kilo years. But this is the time scale over which, given the changes, let's say, of the source at the base, right, over which this whole long-term structure is readjusted. And we can talk more what this, if this, when it makes sense, and perhaps everything remains transient and never reach this steady state, but let's keep it simple at this point. I think I might, I say just a quick couple words before we go to seismogenesis. This slide explores a notion. So people who model the nucleation of earthquakes know that there is nucleation size, meaning that the slip and patch, the preparatory process has to grow to a certain scale, which is called L-nuc or L-nucleation size, before it can become dynamic, before it can grow into an earthquake. And this L-critical or L-nuc, here it is for rate and state, but universally it's inverse in effective normal stress. And we have this wild effective normal stress profile, right? So it means basically where effective stress is small, L-nuc is large, and you may never in fact nucleate. And where the effective stress is large, so where you have your asperity, if you're centered on this stress asperity that we have, that's perhaps where you can nucleate. But you can use this as a proxy, so you could say, okay, if if I idealize the rate and state frictional properties, rheological properties of the fault through the depths, and the only thing that I have to distinguish between different depths is the normal stress, normal effective stress. The fact that this is modulated as 1 over effective stress would create a cutoff for the minimum earthquake size that I could experience. So imagine that we have a patchy fault with a different size of asperities, which produce the background seismicity that we see on faults, right? The microseismicity or small seismicity. So there would be a minimum size of asperity for a given value of effective stress that could nucleate that could go dynamically, right? And this is what this explores. So if I take a distribution of my effective stress, of my asperity, so I can recompute this minimum nucleation magnitude, you could say, or minimum size of the asperity that could go dynamically. And it would look like that. So it's inverse, remember, in the asperity that looks like this, right? So for particular parameters, you can get that the minimum is in the asperity. So you would have a wider range, downward range of smaller magnitudes of events there. And it's about 1 or 0.8. And then you can also look at the number density. So you can assume Gutenberg-Richter statistics, and you can integrate from the known minimum magnitude up, right? To get basically a histogram depth-wise of the number of events. And so that, of course, would mimic that stress asperity, essentially. So this is you could look at this as theoretical inferred histogram. And you could juxtapose this. So this is shown here. So this is the San Andreas. These are the events that are picked up within a certain band of the fault. The colored ones are, I think, two boxes, I think, that Alan Rubin may have used in one of his papers near Parkfield. So essentially here you have histograms. The orange one is for the entire mapped seismicity within this band. And then the blue and green are these boxes near Parkfield. And this is the corresponding prediction based on this stress asperity model. So if it's an indication of the stress asperity or not, but there is some sort of a match. And then you could also ask yourself, could you see this minimum threshold magnitude looking at the statistics? So these are for this for the overall San Andreas and for the blue box. So you are looking at the number of events versus what the Gutenberg-Richter statistics would tell you. And you could see that there is a sort of a crossover magnitude which may or may not be polluted by the magnitude at which the catalog becomes incomplete, etc. But it somehow it is around 1. All right, 2 minutes on the most important message, which is also got 1 minute in the Professor Jolivet talk. So, tale of 3 creepy folds. So, what could it tell us about seismogenesis? And if you probably could guess where I'm going. So, we have a stress asperity that can move around and get flatter with the modulating the flux, right? And so consider a particular case. So this is our effective stress asperity for a particular value of the source. And we have our frictional hydrothermal friction A minus B. So this is actually the one for the gouge from a San Andreas, which was hydrothermally tested by Moore et al. So, well, down to these conditions, but then we sort of can assume how it, what happens to it after. And so, well, I can see it in my screen, but you cannot see it. But basically, okay, there is a stress asperity, and there is what we can call a frictional asperity. Is essentially the part of the depth range where A minus B is negative, where you can actually nucleate and support the earthquake, right? Well, perhaps earthquake could propagate into rate strengthening part, but it can only nucleate within this frictional asperity, right? And so you have your nucleation size, and if the two are divorced, like in this case, they're merely overlap, the two asperities, right? You could see that the nucleation, this nucleation, Rama also showed similar plot. This is this nucleation size, and it's exceedingly large, so it becomes larger than the fold. So this is an indication that perhaps you're not going to have earthquakes. And indeed, if you put it in a rate, if you simulate it, you just get a steady creep at the plate rate. So it's the fold. It's one of those folds that just one of those 3 creepy folds. And then as you decrease the flux, so the asperity grows both in magnitude and in extension depth-wise. Yeah? Alice is doing this. So then you could see that, now you can fit the minimum nucleation length within this frictional asperity, so you would be able to nucleate. And what you get is the Parkfield-like events, you could say. They're limited to this range of overlap between the stress and the rheological asperity. Okay. And then if you close the faucet even more or completely shut it, dehydrate your fault. I mean, well, dehydration may have a different meaning, but we are not putting fluids in the fault. So now for 0.1 millimeter a year, you have huge stress asperity, comparatively speaking, which totally overlaps with frictional asperity. The nucleation, distribution of nucleation length within this frictional asperity, you could see that obviously now you can nucleate on patches that are really like tens of meters only. And so you got this representative earthquake type of cycle with a. And so to summarize, well, we have a mechanism which is fairly simple. It just needs 2 branches for permeability instead of 1, which is the truth, by the way. 2 branches is better than 1. So So with this type of description of the permeability, you recover that you could have that the stress and strength regime develops in such a way which supports all sorts of activity down there, be it slow slip events or tidally modulated stuff. But it also shapes the seismogenesis as a function of the flow rate imposed, right? And so and I think I'll leave it at that. Thank you.
Great. Pablo has a question. I know Alice has a question. So, any students, postdocs on the career? Okay, maybe Kula might go first.
My question is that I agree with something that fluid flow from the bottom, but do you have any idea that where does the fluid finally escape? From the free surface or from the very, very shallow some reservoirs in the underground or those locations that are in your mind where the fluid is finally escaping?
Yeah. I think majority of the time, I don't know if I can go back quickly. Yeah. Well, although here you have a fairly broad figures for this signature of mantle helium, but if you look closely, for instance, for San Andreas, you have things fairly well localized on the trace of it. And then, as I mentioned in the talk, you have these 2 points here, but they actually correspond to splay faults. So it seems like it is fairly localized on a major fault. So meaning that even if the damage zone and this flower structure expands, but I mean again, the flower structure may still be on the scale of a kilometer, right? So on that scale, you would still probably project, yeah. So I imagine that these fluids they can the conduit, or speaking in terms of different language, the fluid conduit site might widen, right? As your fault zone widens.
Okay. Pablo has a question, but recipe, can we go from recipe and then Pablo, Alice, and Silva?
So thank you for the insightful talk. So I got confused. So in your crystal string model, so the stress, effective normal stress is below 3 megapascal. How can I understand the results? Are there no earthquakes?
Well, in this case, there were no earthquakes, yeah. So this case correspondence, it was, so you could see that the stress, the normal effective stress is divorced from where you can nucleate earthquakes. So the nucleation size is basically larger than the fault, and in this case is just of a seismic fault, creeping at whatever rate, far field rate is imposed. Right, and then this is the case where you have earthquakes, right? But both of those cases, they are common in what happens down deep, right? So the pressure is near lithostatic at the source of the fluid, and how far up along the fault these overpressured, very high overpressured conditions persist depends on how much is the flux, right?
Looking at this figure and assuming that the stress drop is proportional to the effective monostress, this model seems inconsistent with the observation that the stress drops of earthquakes are not optically dependent, or not strongly dependent on depth.
Yeah, that's a good question. I'm not sure, but you're talking about static stress drops. Maybe statics are different from dynamic. Maybe they're all recovered by some sort of a restraint. But I mean, I would have, I'd like to look at this. Yeah, I don't know much in a way of answering this.
I think my question is related. So the observations that motivate this study, okay, first of all, it's a great talk, and I'm looking forward to the papers. But so the observations that motivate is they're happening on faults that produce earthquakes, lots of earthquakes. And it's been shown before that if you're assuming rise 92 very high pore fluid pressure conditions, the stress drop could be almost complete, and you get a lot of stress rotation, for example, and other interesting effects due to co-seismic slip. So the implications for rupture dynamics of co-seismic slip are, I think, quite well understood, and they imply a lot of reorientation of the local stress field, a lot of variability between each side of the fault, and all these kind of things. It makes it very unlikely, in my view, that you would have a persistent asperity that could sustain this. And I'm also wondering, this fault has to, or this theory has to support everything, the aseismic behavior, but also the seismic conditions. So I'm wondering how this fits together.
Yeah. So I could downsize the message and say where in my view, it would be totally applicable. If you take a seismically creeping fault, where everything is in action, the permeability is refreshed all the time. So perhaps this long-term steady pore pressure regime view is, I would say, it's probably given the source, it's inarguably should be there. What happens on a cycle, so whether the long term as described here actually corresponds to or reflects well the transiency that happens on a this time scale of a cycle, it's a great question. So, and I think that has to be addressed. So what I could say is that permeability is essential. So permeability is created in a way by the source, by the amount of flow that tries to get through, right? So in a way, it's not a material property per se. It's modulated based on what flow is. So if you assume that the process that this flow could get to a steady state, then basically the flow maintains the permeability, meaning that even if the fault is not slipping, then perhaps it creates some sort of a small strain rate within the fault gouge, etc., to be able to refresh permeability if it's been healed, etc. I don't know if that's what you were thinking, but yeah. So it's not meant to solve all people questions. I mean, it's meant to be some sort of a baseline, but it's a simple physical and with some interesting intuitive results model, and then one would have to explore what happens to it if, let's say, you look at these changes of absolute stresses through stress drops and stress rotations, as you say, seismically, and regaining of that interseismically, as well as what happens with the healing and the refreshing permeability and so on. Some of the work in the Eric Dunham's group, along. Well, but Eric Dunham's group is using the Jim Rice as a base. It's a Jim Rice single branch permeability. So his base the long-term steady state pore pressure profile would be the one that corresponds to this high plateaued effective stress, which comes off here and then goes down like this. Right?
Okay, so I think we have time maybe for short questions. I don't see anybody had and also I can.
So as far as I know, and seismologists correct me if I'm wrong, but there's no limit size of seismicity. Stay there. So there's no minimum size of earthquakes at any depth.
Well, I have an answer to it, I think, to this question. I think that one is an easy one. So what's been discussed here is some sort of a macroscopic stress and effective stress profiles, right? But then if we talk about background seismicity, so we think that it happened on a smaller scale, mesoscale patches, right? That could be rheological or whatever. Or they could be normal stress patches due to the roughness, right? So this is not considering this high frequency, spatial frequency roughness of normal stress that could enable the small patches in an otherwise very that would be otherwise in a very low effective stress regime, you know, somewhere here or there, to rupture just because they experience locally very due to them being an asperity, an actual topographical asperity, let's say. They experience larger normal stress and therefore a larger effective stress than this macroscopic profile. So I guess this is, but I would imagine you would still be devoid. So it's not like you can completely cut off seismicity going down in size, but statistically speaking, I imagine you would be devoid of, you know, you would have diminished, I would say, seismicity.
Okay.
Yeah, so back to the permeability. So one thing here is you've got this continuous flux for thousands of years from the base of the crust, high temperature, high pressure, up to the surface. That's going to clog your permeability really quickly, right? Because you're going to have that's almost bound to be reactive. It's going to want to precipitate stuff. So what happens if you can't maintain the permeability to maintain the flow?
Well, then it's essentially a question of whether, whether you could have this stable regime or instead you go in this intermittent instability like a fault valve one. So would it still look on average like that? I think it's a question to be addressed. Yeah. But in a sense, so what I was also trying to say, that one should really investigate it, because even if the whole thing is not appears to be locked, could it be that you still entertain some strain rate within where the fluid wants to pass to keep refreshing the permeability, right? So that's why I say if you have a seismically sleeping fault, then I think principally you don't have these issues, I think, with interpreting this, yeah, because you are refreshing.
Okay, a quick question. So you argue that your model is explaining the depth distribution of hypocentrics
Yeah.
for the San Andreas fault. Your model holds only for the San Andreas fault. You need to have two going, I mean, a fault going through the crust.
Yeah.
But most of the earthquakes that we use to draw these histograms of depth distribution, they are not on the San Andreas fault. They are on everywhere.
No. I used the spatial band. Yes. So what was the question? I just used those ones near the trace.
Yes, but if you take the other earthquakes away from the fault, they will show exactly the same distribution.
Yeah. Okay. We should think about it.
Okay, let's keep the discussions later, and then just keep the time. I know we're late
Sorry.
now, but
Would you like to use
our
it?
next speaker is Lucile Costes, and
So this one
he
is
is talking about
well.
what controls SEC at intermediate depth in subduction zones.
Sorry.
Comme ça. 1, 2.
Voilà, comme ça.
1, 2, 1.
Ouais, je pense
Ouais.
que c'est pas mal.
This is working. Yes.
T'as
Okay.
le laser ou tu peux passer les slides?
Ouais, je vais faire le laser. Okay, so good afternoon. My name is Lucile Costes. First, thanks for the organizers to give me the opportunity to present my work. So I am supervised by David Marsan and Blandine Gardonio in Easter. I am interested in intermediate depth seismicity. So we are in subduction zones at depths greater than 50 kilometer depth. And so at those depths, seismicity is occurring inside the slab, not on the interface, as it is not seismogenic anymore. And the main problem of this seismicity is that at such temperature and pressure conditions,
we do not expect brutal failure. Yet we have an abundant seismicity, so we need a mechanism to explain it. And two of them are dehydration embrittlement and thermal shear runaway. This second one is less evident to observe, and so usually we go for dehydration embrittlement, in which hydrous minerals of the oceanic lithosphere undergo metamorphic reactions, which releases fluids, and then the faults are brought closer to failure. So I'm focusing on a particular aftershock sequence which followed the magnitude 7.1 2003 Miyagi earthquake. So it is located in northeast Japan, and it is just below the coast of Miyagi Prefecture. And as you can see on this cross section, it is located inside the slab at about 70 kilometer depth. And if we zoom in and look at the early aftershocks, we see that this inverse earthquake broke both the crust and the mantle of the slab. And finally, you can see on the map that we are really close to Tohoku earthquake. And well, we know that its afterslip occurred just on the interface above the aftershock sequence. So they might be related, but well, we'll see this later. And we can wonder why I am studying this sequence. Well, we have several questions for which we would like to find answers. The first one is so the mechanisms for intermediate depth seismicity. And we have access to different tomography studies. For example, this one, which is passing by the hypocenter. And we have velocity anomalies, which indicate potential presence of fluids. So this would support dehydration embrittlement. And by studying this aftershock sequence, we would like to find a fluid signature. That's the second topic on which I will focus my talk, is the current active debate on the intraslab seismic activity after Tohoku earthquake. For example, Delbridge and Zay et al. Consider that after Tohoku earthquake, there is a high increase in seismicity in the upper plane. So you can see this on this red curve. But Wimpeny et al. Consider that this increase is only due to aftershocks of events that are intraslab themselves, so not linked directly to the megathrust. This is an important question, as it can be related to the state of stress inside the slab and whether faults, intraslab faults, are strong or weak. And just finally, on a broader view, Bouchon et al. Found lineaments of seismicity before Tohoku earthquake, which our main shock here in green is part of. And so maybe it could be part of the preparation of Tohoku earthquake. But we won't look at this today. So to go back to the aftershock sequence, I plot here a 3D plot of the seismicity where you have the slab interface, and you can easily recognize the aftershock sequence, which is well aligning along the fault plane. So it is also well defined in time, so I could well constrain it. And I choose this red box as the study volume for the following. And another good point of this aftershock sequence is that, unlike most of intermediate depth earthquakes, it has a high aftershock productivity. So it gives us more data, and we hope that we can extract useful information from it. And finally, as you can see there, we have nearly a perfect fit to the Omori-Utsu law before Tohoku earthquake. So you see the data in blue and the model in pink. And it is also occurring after Tohoku earthquake, so any deviation from the model will describe meaningful processes. So this is what I'm doing here. I'm looking at, first, only at the interface, so the yellow part here. And this time I'm in a log-lin scale. And we fit the Omori law up to Tohoku earthquake, so here in pink, sorry. And we extrapolate the model after. And if we compare with the non-fitted data in red, we see that we have a significant increase in seismicity right after Tohoku earthquake that is lasting for about 2,000 days. if now we look at the intraslab part, so first in the crust, we don't see this increase anymore, and neither in the mantle. So the first result is that the intraslab is not behaving as the interface and is not reactivated by Tohoku earthquake. This result is quite surprising because, as I told you, we are near Tohoku earthquake here, and we know that this megathrust has disturbed all the subduction zone. And I also calculated the Coulomb stress change on the Miyagi fault, and I found several bars of Coulomb stress change. So it should be enough to create seismic rate change, which is not. So well, to go further, we decided to look at the stress field inside the slab. Well, we can't have access to absolute value of stress, but we can have rotation between before and after a perturbation. For example, on the interface, Hasegawa et al. Found a rotation of the stress field of about 30 degrees due to the occurrence of Tohoku earthquake. So I'm going to do the same, but for my aftershock sequence in Intraslab. And so the idea is to inverse focal mechanisms to get the directions of the deviatoric stress components. So for example, so I begin with mechanisms before Tohoku earthquake, and I get those stress components represented here in the stereonet plot. You have here the corresponding beach ball plot. And so sigma 1, for example, which is the most compressive component, is subhorizontal. And now if I do this with the mechanisms after Tohoku earthquake, I get those stress components. And well, we don't see any difference, and I measured a rotation of about 1 degree plus or minus 3 degrees. So we cannot resolve any stress field rotation in the intraslab area, at least in our aftershock sequence. And so we have two possibilities. First, the area is mechanically isolated, and so there is no stress change on it. But like it's a naive possibility, and we can't explain it with a realistic mechanism. And so the other possibility is that we have a stress change, but the aftershock doesn't respond to it. We can explain this one with considering that the stress which was already in place before Tohoku earthquake was already very high, so the stress change is negligible in comparison. And this means that the fault of Miyagi earthquake would be strong, but it is inconsistent with presence of fluids. So for the moment, I don't really know what I can get from this. And I will just add a final result, which is interesting. We applied the ETAS model to the aftershock sequence until up to Tohoku, so we have no disturbance. And we did this by distinguishing the pre-productivity factor for the main shock and the aftershock. So the main shock is the big K in red, and the aftershock the little k in blue. And we found that the main shock is about 300 times more triggering than the aftershocks. And this can be translated in 97% of the aftershocks are directly triggered by the main shock. This is, again, really unusual. Usually you have quite the same values for main shock and aftershocks triggering. And so it is like after being launched by the main shock, the aftershock sequence is just following his life without any perturbation, and neither coming from inside from the aftershocks or outside the Tohoku earthquake. And so to conclude, I hope I have convinced you that this aftershock sequence is an ideal case study, like a natural laboratory to study intraslab and intermediate depth seismicity. But I have, in my interpretation, I have a contradiction between considering that it is a weak or a strong fault. Weak fault because we have a very long-lasting aftershock sequence, we have a lot of aftershocks, and the velocities anomalies. but we don't find any perturbation from Tohoku earthquake. And finally, we have no aftershock self-triggering. And so currently I'm running template matching to ensure that we have a good resolution on seismic rates, and notably after Tohoku earthquake. And we hope that waveform analysis will help us to have new insights in this. So thank you for your attention, and I hope we can have fruitful discussion.
So questions? Roland, Anton, and Caroline. So Caroline, you want to go first?
Okay, thank you for your talk. I was wondering, because you said at the beginning that the Miyagi earthquake was itself kind of special for having produced a lot of aftershocks
Yes.
for an intraslab earthquake.
Mm.
And do you think that's also related to the fact that its own aftershocks are not producing a lot of aftershocks, like itself? There's something.
I don't know. We have only a few big aftershocks. Like the maximum one is magnitude 5, so it's quite low in comparison with what we expect. And so this can explain also why we don't have a lot of triggering by aftershocks. But I don't think, I think the fact that aftershocks do not trigger their own aftershocks is a reason why we have a good productivity. Like it would be even the contrary. Yes.
So Roland, Anton.
Really exciting result. Have you tried to look at the events outside the aftershock zone to compare, right? Is your
Not
result
yet.
still, not, contradicting what previous studies have found?
Yes, it is.
Could it be?
It is contradictory with other studies which
But
are.
in the sense of this using different events, because you focus on, right, one of your possibilities was, well, maybe there is something special
For this,
about
yeah.
that particular area, where it is, or what properties it has.
Well, I don't know. Well, most of studies are much larger scales, so they find perturbation by Tohoku. And so you would mean that we would look at seismicity just around, or the aftershock sequence.
Systematically, right, compare what you find in the aftershock zone of this event, right, which gives you that special opportunity, but then also expand it to the area around it,
Okay.
larger area, to see if using exactly the same approach you do.
Okay,
you
I could try.
Get a different result than that.
Yes, I could try, but I don't know if we have enough seismicity before Tohoku earthquake, like in the surrounding.
Yeah.
So, but I will try.
I have the same question.
So, okay.
Very interesting. So do you also observe all fault aftershocks, or are these all on the same fault plane, including the ones after Gong?
Well, for the moment, we only see this big group aligning along one big fault plane, but yes, it's really planar, and we are going to relocate everything, and we hope to see more precise structure, maybe. Yeah.
Okay, so thank you, Lucile, for our next speaker is Gong. So he will talk about Rupture Net 2D, which is a deep neural network for dynamic rupture simulators.
Hello everyone, my name is Zekang Gong and I'm an undergraduate student from Sichuan University, China. And I'm presenting today is a simple work, deep neural network based surrogate model for dynamic rupture in 2 dimensions. And in this work, I work with another undergraduate Ziyi and supervised by Chao Liang and thank for them. Oh, so as we know, the earthquake doesn't happen on the single point, but on the fault planes with finite dimensions. And during earthquake, slip on the fault propagates dynamically from the epicenter to the rest of the fault, and radiates the hazardous ground motion at the same time. And simulating this process is not only important for the seismic hazard assessment, but also important for understanding the earthquake physics in general. So to simulate this process, we need to solve the elastodynamic deformation, the solid rot, and the friction loss on the fault interface. And it's a really complex process which has been talked about yesterday. And this process normally can only be simulated numerically, especially for very limited special cases. So far, there are lots of numerical methods developed for simulating this dynamic earthquake rupture, like the spectral element method, the phenomenal element, and so on. And what they do is to take the fault stress and the fault geometry and the material properties and fractional parameters as the input, and through some computation output the fault stress, the slip on the fault, and also the ground motion, the seismograms, and the displacements on the inner solid domain. But this numerical code has 3 major limitations. The first one is they are usually computationally expensive, especially in 3D, and they are normally non-differentiable, which means you can't compute the derivative of the output with respect to the input, and you really need a refined grid for accuracy, and the time step is also limited by the CFL condition, or it will be unstable. So because of these limitations, inverting for the dynamic parameters are ready to change. As a result, most current understanding of the earthquake rupture dynamics, rupture process is learned from the kinetic source inversion, but it has a major problem that the regulation and the smoothness constraints applied to it is not physics-based, and thus it doesn't reveal the fractional parameters, the dynamic parameters on the fault. So, but why we need the dynamic parameters? Because we are not only interested in how a certain earthquake just happened, but we are also interested in how why it developed as it was, and what it will do during next earthquake. So the fractional parameters are necessary input for the physics-based predictive models. So what's our options? We can still to optimize the codes and to speed it up with sampling-based methods like the Markov chain Monte Carlo methods, and it's effective, but still computationally expensive. And the second choice is to use the adjoint-based inversion combined with the gradient-based methods, but it can significantly reduce the forward numerical simulations, but it's not always ideal, especially when dealing with nonlinear fractions. So what I presented here today is a neural network-based surrogate model for the numerical codes. If the neural network is well trained, it can be accurate through approximately, but really fast and differentiable. Thus, it gives us option to use either the MCMC or the sampling-based methods, or the adjoint or the gradient-based methods, to achieve a more efficient dynamic inversion. And to build a neural network to predict the entire evolution of the sleeves or the slurries or other state variables is really challenging, especially in 3D. So we start simple, and so we work with 1D linear sleep awakening folds and embedded in a 2D homogeneous elastic solid, and instead of trying to predict the whole evolution of the sleep on the folds, we just predict the two key parameters: the rupture time and final sleep, which means when a rupture front arrives at a certain point and how much sleep occurs there. So what we need to do is to take the stress distribution on the folds and the fractional parameters as the input, and output and through our neural network output the rupture time and the final sleep, the two parameters, and we discretize the fold into 100 elements. So the input is a 5 by 100 array, and the output is a 2 by 100 array. Now we have very well-defined and simple end-to-end supervised learning approach. And the neural nets need to learn the mapping. And to generate a large enough data set, we use a boundary element codes developed by Algorithm, and in the data set, 70% of samples are used for training, and 15% for validation, and 15% for testing. And here are some samples from the test set, randomly drawn from the test set, and you can see the neural network successfully fits the final sleep and the rupture time, and how it propagates in both directions, and how it accelerates and decelerates. And here you can see the neural networks successfully identify the supersharp transition here, and when the rupture propagates into a zone with a negative stress drop, it arises and still penetrating a distance into that zone. So regarding the accuracy, we use two metrics: the relative absolute error and correlation coefficients, and overall the relative error is low for the uniform distribution, and it increase as the complexity of the false rupture increases, as in the 1 aspérity and 2 aspérity scenarios. And if you look at the correlation coefficients, it's less prone to the outliers. And regarding the model efficiency, the numerical simulation usually costs about 2.5 to 200 seconds, and neural net takes about 1.5 milliseconds, which means approximately a 3 to 5 magnitude of order speed up. And the comparison may be a little bit unfair because the two approach take advantage of two different hardwares, but we can still feel a sense of the speed up in this approach, and similar speed up factors have been reported in other physical problems. And here we show the prediction on the unseen longer fault. So unlike the numerical methods, it can handle with arbitrary input parameter space. The neural network is trained on a finite data set, And in our test and in our training and validation data set, the neural net only has seen the faults with lengths of 20 kilometers to 60 kilometers, and we have to predict the faults with lengths up to 200 kilometers. And even within training set range, the performance also decreases near the lower range. That means our neural net maybe doesn't explorate well. And we also test the effect of the data size and the model complexity, and we test about the data about 50,000 and 115,000 and 300,000, and adjust the neural network complexity by change the number of units of the transformer, and we can see for the more simple rupture, there are smaller data and a simple model is sufficient to fit them. And for the uniform distribution, about 1,000 simulations data set is enough to get a strong performance. And for the more complex structures, we also need large data and more complex model. And to sum up, we have developed a simple neural network-based surrogate to predict key source parameters of the rupture dynamics in 2D, and the neural network accurately predicts the two key parameters, and the neural network provides a promising acceleration strategy for dynamic rupture simulations and also the immersion. But our model has limitations, and the current model does not produce the full space-time evolution of the physical variables, and the model is still in 2D, and we need to move into 3D, and it's still not ready to connect with the real observation. And to connect with the observational data, we are working on to add 3 additional parameters for about the sleep rate. It's about the peak sleep rate, the rise time, and the time sleep rate, and the time sleep rate to rise to peak. And we simplify the sleep rate function as a combination of a linear part and an exponential part with 1 or 2 peaks, and we constrain the sleep rates by integrating over time to match the final sleep. And with the sleep rate function, we can integrate it we can calculate it with a given range function, and we can get the waveform to connect with our real observational data. That's all. Thank you for your attention. No, we just working with the sleep rates and didn't.
So your results only give the final sleep or like the sleep history?
No, it's just final sleep and yeah, but yeah.
You will do it later, like in the future?
Because we are more interested in the immersion, and what we care about is to constrain the fractional parameters.
So my question is actually last part. So do you try to do the inverse problem for your deep learning technique? Inverse problem. This is because
Yeah. This is a forward problem, and we did, and it's also in 2D. So currently we can't to do the inverse problem right now, but we are working on it.
Okay, so is it in optimistic? Do you expect that it succeeds very well, or that, because I guess there's much more trade-off between the trade-off in the parameters maybe.
Oh.
So do you have any expectation that it goes well, or do you have some difficulty? Do you have some idea of that? Not data. It's not data.
Sorry, I didn't understand.
Do you think like it works pretty much well if you try or not?
Oh, I see.
No. So you expect that you will succeed on the inverse model with your deep learning approach.
Oh,
Sorry, you got my question.
so there are many models for the inversion using ping, and for the rupture dynamics is more complex boundary conditions on the faults, so it's maybe hard to use the PIN to do the inverse problems. So yeah.
Okay, so yeah, it's gonna be easy.
And Brittany, the last question.
Hi, thank you for your talk. I'm still skeptical of machine learning methods for forward problems, and I was wondering if you could explain, like, you trained it on 300,000 forward models, right?
Yeah.
How long did that take?
It's a very long time. Training time is about our training data set is about 0.3 million. So it's about 2 days or 3 days on A100. Yeah.
So if it takes 2 to 3 days of training, and then you sort of get a surrogate model that can do a forward pass or evaluation in like a couple milliseconds, I think you said.
Yeah.
Versus a sort of a new forward run using a traditional method that takes maybe 100 times that or something. I forget what the speed up was. Was it 100 to 1,000 times speed up? I guess what I'm wondering is, is it worth that 2 to 3 days of training time?
Yeah.
Like, it'd be nice. I can't do any math right now, but like, you need to figure out, like, was it worth the 3 days for 300,000 simulations to get that speed up for a simple forward run?
Yeah.
You have just stayed with your finite difference method, right? And I guess my sort of additional question to that is, like, well, when you say it's like 1,000 times speed up, you're talking about like a forward pass. So after you've trained it, right, like you do get a lot faster of a surrogate model. But I guess the question that I always have with these, and I've worked in this area too, so I sort of am asking myself that, is like, you want a surrogate model to which you can evaluate, say, for different parameters, right? And I don't really know, like, in what scenarios in which you might want to have like a really fast surrogate model for, like, say, a different parameter set. And surely there are applications out there where you might just like say, okay, I want to like evaluate my surrogate model with these parameters, and I have a much faster machine learning method model. But I don't know where those exist. I'm not a seismologist either, so I'm saying it from a standpoint of ignorance.
So actually.
For instance,
In the lab?
yeah, we have a time span for see something that is like 1,000 of times smaller than and let's say you want to see a seismic cycle, and you want to predict fast how is moving the wave inside a sample. Well, have the possibility to go down of that kind of amount of speed. It means you can try to monitoring time by time.
Mm-hmm. And so you might have like many of those you might want to run?
Yeah,
Like
maybe
tens of
you
millions?
want to run
Sorry.
run each, you want to run it on 1,000 kilohertz.
Okay,
So just see continuously what's happening.
okay,
That's actually a problem that I have.
okay.
Like,
Great. Yeah. Yeah, like I said, this was from a point of ignorance, not a point of criticism.
Okay, thank you so much for the great discussions. So our next speaker is Tian Lu, and she's talking about deep learning in microseismicity and aftershock sequence analysis.
Is the still function? Okay, I'll take it. Hello? Okay, the last talk, so I made my slides a bit more colorful to attract your attention. So if you feel overwhelming or hungry, I hope you can still flowing. And I'm Lu from ETH. I'm in second year of my PhD. And today, I'm actually gonna talk less on the technical part of deep learning, but of course I'll make sure that we'll talk about it. But first, before that, I want to show some interesting results that, or seismicity patterns that we see freshly from the experiments that newly happened. Okay, this is not working. Okay, for the motivations, I guess I don't have to stress more from here. This is the questions many of us are wondering what happens when a fault activates in detail. And we want to study all these questions, and they are very basic first-order physics questions, but in observations, we are always lack of resolution because we're too far away or do not have a direct observations. So the question here I want to ask is, can we resolve the rupture physics of real earthquakes? The answer is probably if we put sensors directly on the fault. So, what happens? Okay. And then I'm gonna introduce where were our experiments happen. So we are working at the Bedretto lab. As you could tell from the name, it's from the Italian-speaking part of Switzerland. It's an underground laboratory, and for the main part, this was over a kilometer overburden of granite, and so we are getting closer to the seismogenic zone, but still kind of shallow. And then it's there's also the dominant rock volumes in the Swiss Alps. Always jumping. Sorry for that. And here I'm listing two major test beds in our case. So here in the shallower tunnel part, there was the geothermal reservoirs, and then on the right side, the blue one is the earthquake physics test bed that we study here. And the unique part of our earthquake physics testbed is that we do have a natural pre-existing fault zones. So this motivates us to study what if we induce earthquake here. And to do that, first we need to identify and characterizing for the target fault zone because it's super complex and it's intermediate mature fault zones. So it's not a planar fault, but with small micro fractures around it. And then we plan to, or kind of in the way to densely and closely instrument it with, of course, seismometers, high-frequency seismicity sensors, and also in the fiber optics of distributed sensing, and also like sensors to measure the 3D displacement tensor directly at the injection point in the boreholes. And with everything ready, the target is to make it move. So our target here is to induce a moment magnitude of 1.0, roughly earthquake, and to study its rupture physics. So this is so-called the FAIR project. I know many people have already heard it. So it's short for fault activation and earthquake ruptures. So we've already talked about what this is about. And some more detailed plans will happen after this November. But before that, what we could do is we have mentioned this geothermal testbed, which is not far from the new places. And we did in this April is called the magnitude or M0 experiment. So we were targeting for moment magnitude 0 events or main shock here. And we've already had many preliminary tests from the geothermal reservoirs. And the reason why we cannot do it here because it's this from last weekend that we only have 12 meters in the tunnel yet, so it's not ready there. And now we gonna talk more about this zero experiment. So we are making use of the we're instrumented geothermal test bed, and we have already understand a bit for the seismicity pattern and the structures from previous experiment as a reference. So here's our injection protocols or the pressure. And we want to study also here the preconditioning schemes, which means from previous study we found that like below 20 megapascal it will follow with minor seismicity, and after we increase the injection pressure we will see a huge increase in the seismic rate. And here I'm listing the seismicity patterns at the time range. So here is we see the preconditioning phase with 15 megapascal injection rate, and here we do have some seismicity. We will look at the spatial distributions later, and just when we increase the pressure, we see from our previous experience that we have much more seismicity. And before we always like stop when we reach some higher magnitude, but this time we just keep injecting until we get this one here. So here I'm showing the main shock with this normal faulting focal mechanism and the 10 minutes of aftershock sequence. We could see that in the cross section, the aftershocks fits quite well into the same plane of the normal faulting directions, and they're like this large direction and some small details of this connecting small fractures we're still studying at this moment. So the result here is after 18 hours of high pressure injection, we got the main shock of moment magnitude minus 0.4, because the moment magnitude came a bit later. We had to stop the experiment, so this is a bit below our target, but we did have the main shock, and we could also see a very active aftershock sequence. And with the standard method, it's with like before the deep learning catalog, now we have already over 10,000 of events relocated. And we also could see from the b-values spatial distribution that the main shock located right at where it has a low b-value anomalies from like which also consistent from previous injection experiments. Here's animation of it. Maybe we don't have time to look the whole videos. And so here I started from the preconditioning part, so we can kind of ignore what happens before here. And we could see even with minor seismicity that this seismic event is already full of the whole volume. And if we speed up, I don't know if I can, yeah. So now we at the point that we're gonna increase the pressure. So you could see that much more seismic event has happened. It doesn't last long until the main shock, but I'm gonna make it manually. So you see, focus on this area for a bit. And sorry, I cannot do both at the same time. So you see here is the main shock. It's very fast because we just shut in after the main shock at the midnight. The question here is that if you remember from the seismicity time series, there was nothing more than magnitude -2 before the main shock, and then suddenly we reach the main shock with a gap. So here I'm plotting the cumulative seismic moment. And of course, we're gonna ask ourselves that can we reproduce this similar large magnitude event? So the answer is that we can do it again. So we repeat this experiment, but this time we want to also test how the preconditioning, so with the, we don't inject before with the low pressure water and just directly inject with the high pressure water, how would this evolve the seismicity. And here I'm again showing the time series. So here the results from the time series that the seismic event rate has been increased without the preconditioning. But we don't have this large event. So we keep injection with a longer time and with larger volume in this case, but we have the largest event of moment magnitude minus 0.74, but nothing else. And if we compare the spatial distribution, that we could see a more clear migration if we don't have the preconditioning. So yeah, here is just to compare the cumulative seismic moments as respect to the hydraulic energy for those two experiments. So the lower one is the first experiment, and here is the second experiment. We have several a bit larger events, and then you could see it started with the steeper slope until here at this point that the first experiment with the main shock kind of catches up in the seismic moment. And now I'm going to talk about the aftershock sequence. Just from the drawn plot, so here is like the historical seismometer that we plot from the pen, and then you read line by line, and this is the main shock, and you could see directly from our eyes, like without the machine learning, that there are like a large amount of aftershocks. The motivations here, I guess, has been already mentioned several times, and I'll be fast here. In our case, it's even smaller, like picoseismicity, we are facing more challenges from the high frequency part, and also with our acoustic emission recordings, it's only single component, so it's especially more challenging for S-phase detectors. If we want to know how much events has been missed by the traditional method, so here I'm showing with the right, the triangles are the events from the SESCOMP, so it's the traditional catalog that we have. We could see that it picks some, but there are much more details behind it. And if we wonder what happens if we use the machine learning pickers, that's it. So the blue ones are the P onset, and the pink ones are the S onset. Here I'm using a bit more aggressive way so that the phase association can hopefully clean this mess a bit more, but we could see that now we do have more S peaks, before we only have P peaks, and also with the smaller events, so we can have this picked up, but before there was just quiet in the traditional catalog. Here's a bit more details that we're using the UNet. The input is the raw waveforms, and the output is at the same time series, but likelihood of the onset. It's just showing some performance of our models. We have separate P and S peaking models, and P can perform much better as we expected, but both looks quite nice. And if we project this onset arrow to space its submeter arrows, and we also have a separate model for force motion polarity. So if we detect the P and then we zoom in to detect for the force motion polarities, here we're producing the probability. So it's not only a single up or down, but it's rather a probability distribution. So our goal here is also to include uncertainty quantifications, both from the onset time to the location, and also from the first motion polarities to the focal mechanism. This is more about what we did for the onset time calibration and uncertainty quantifications. If you want to know more details, I'm happy to chat for this technical part. So here we don't include more computational complexity, and it's quite easy to be implemented in our workflows. This is it, the deep learning catalog that I plotted for the aftershock sequence. So here is the main shock. I think there are some dots that's not so visible. So behind we could see these gray dots are the additional ones from deep learning catalogs. If you want to see more details, we can talk about it also. And this is just from the phase peaking directly insert into the traditional monitoring real-time pipelines. So we do need more efforts, but we already see twice of the amount of events in this 10 minutes aftershock. That's my conclusions, and I think I'll stop here. I'm happy to answer your questions.
Thanks for your very nice talk. I was wondering, so you showed that in your two experiments you had different results, and you attributed that to the fact that you had preconditioning in one of them and not in the other.
Mm-hmm.
So I'm not into seismicity expert, but I think that in a lot of cases you don't necessarily get the same outcomes, even if you do kind of the same injection stuff.
Yeah, we will have the third one, just to repeat what we did for the first. And it's not the only reason that or cause could be. We also look at the ambient pressure from, there's a precipitation, of course, in August. So we have ambient pressure 0.1 megapascal higher than the April. So, this all can end up, so we need to study more. This is kind of very preliminary. Yeah.
Thanks.
Thank you for your talk. You mentioned or said on your slide that the main shock occurred within a p-value anomaly, I think. I'm just curious, what were the kind of values you had for that? What p-values?
Was not the one to made this, but I put.
This is linked to one of the beginning.
Yes, but I put one p-value here because I don't have time to include that much material. So this is the spatial distribution of p-values, and then you could see here is the boundary of the lower anomalies, and it's also consistent with previous experiment. It doesn't change in this experiment.
You can see the color bar is 1.2 or something.
Yeah, I can see it. I just missed it. Thank you.
Okay, great. That's the last question of the day, but we can talk afterwards. Yeah.
Oh, I was wondering, on the dropout, I don't know what a recurrent neural network is, first of all, but for the dropout am I understanding it right? You just basically remove a neuron and then see sort of how well the model predicts something?
So the dropout was a kind of very usual technique in neural network training that to make the model more robust and less overfitting. And we use dropout not only in the training but also in the inference stage, so that we reproduce the multiple passes several times with random dropouts and see how the outputs vary with each other. So that comes up with uncertainty, posterior distribution.
And do you have to start with a certain amount of neurons to make sure that you have sort of enough complexity to where you can?
No, we just set a percentage and it's totally random.
Okay, great. That's all the speakers for today.